Make sure you do have your periodic tables out. And finally, this is the beginning of the best part of chemistry. Starting to talk about moles. Finally. You're not a true chemist until you know what a mole is, and if the first thing that you're thinking about is a fuzzy little critter that digs up your yard, you're not a chemist. Or a what?
An ugly mark.
An ugly mark? Oh, yeah, sorry. Yeah, I didn't think of that. I'm always thinking of the little blind critter. Alright, so, and the bad news, the majority, like 98% of this stuff, is math.
Yes.
I know. The test will have 0 concepts on it. Okay, so
I might get a good grade.
I know it's all math. It is all math. And the nice thing about this too is we're going to be using some big numbers, so make sure you know how to use. These are some. All right, so here's some vocab. You can take a look at that at any time. All right, so the first thing that we have to talk about with a mole is, number one, what is a mole, or how big is a mole? Okay, a mole is a standard method in chemistry for communicating how much of something we have. It could deal with how many atoms, how many molecules, how many electrons, how many cats, dogs, whatever you want. Okay, if we talk about mole, it's a certain number. And hopefully I have that number up here somewhere. Oh, here it is. Yeah. Now, with this, I'm not going to read this to you because it'll make sense once we actually start doing it. And I think all this does is confuse you. But what I really love, I mean, I'm serious when I say this. When you want to abbreviate mole, drop the E. Okay? If you want to abbreviate mole, or if you want to write it out, normally if you're going to abbreviate mole, you put MOL. Don't just put M, because that could represent either meter, milli. But if you're going to abbreviate mole, drop the E. And some of you might say, is that really a time saver? Actually, it is. You'll like that. That E stroke is nice. Okay? When we talk about this number, 6.02 times 10 to the 23, this has a name. It's called Avogadro's number. Now, some of you might say avocado. No, it's not a vegetable, but Avogadro. This is the guy or the person that actually came up with this constant value whenever working out these problems. Now, do you have to know the name? No. Just make sure you know that number or recognize that number. And I think I have it on the back of the periodic table too, so if you forget that. But hopefully you'll use it so much, this topic, that it'll become embedded in your brain forever. Alright, let's see here. I often like to think about talking about how much a mole is. Okay. And when I say that is, if I had a mole of dimes, okay, I have a dime here. I'm a very rich chemist here. But if you lay the dime on its side, does anybody know what the width of a dime is? One what?
Millimeter.
1 millimeter. Okay. So the dime is, I don't know why, but for whatever reason, our government decided to make the dime the same width as a millimeter. So if I take 10 of those dimes, and I'm not showing off here, all right?
Centimeter.
Okay, we have a centimeter. So and this is 10 dimes, and I would say that most of you could see those 10 dimes in the back. You might be hard pressed to see the 1 dime thickness from the back, but you might be able to see the 10 dimes. Okay, so that's equal to 1 centimeter. So if I took those dimes and made a perfect column, and I had Avogadro's number of dimes, the length of all those dimes in that column would be 3.74 times 10 to the 17 miles.
How many miles is that?
That's 3.74 times 10 to 17 miles.
Miles?
Miles. Okay.
A mile is a...
Pretty long, yeah.
So how is 10 dimes?
No, 10 dimes is a centimeter.
Oh. 1
mole of dimes stacked on end to end, okay, kind of like how I have them stacked like this.
So how
Okay.
many are in the
So there's 10 right there. That's 1 centimeter. I'm not saying stack this way. I'm saying this way.
It's tip over.
Well, you got to be careful when you stack it.
Wait,
Okay.
so
So here's my question. How far is that?
A lot.
Okay. So 3.74 times 10 to 17 miles. How far is that? Well, 9.3 times 10 to the 7 miles is the average distance from here to our nearest star. 93 million miles. Okay. Are we about halfway there? No. Okay. 3.7 times 10 to the 9 is the average distance from Sun to that rock, which used to be called a planet, Pluto. Okay. Now remember, we're not even looking at all those dimes yet.
how many dimes are there?
How many dimes? 6.02 times 10 to the 23 dimes. Okay. So if I had 5.9 times 10 to the 12 miles, that's the distance light travels in 1 year. So again, if I had all those dimes stacked up, we're not even there yet. So it would take over a year for light to travel. 1 mole, or 6.02 times 10 to 23 straight column of dimes, which equals 3.74 times 10 to 17 miles, is equivalent to 63,400 light years long. And you're sitting here going, well, how long is that? Honestly, if I can't run it or drive it, I have no idea what that distance is. Our Milky Way galaxy is only 40,000 light years. So that stack of dimes, if I had 1 mole of that, would go way across our own Milky Way galaxy.
That's so long.
So, let me put this into perspective. If the thickness of 1 dime is this big, okay, and if I bet you if I filled this up with water, it'd be really close. I'd have a little over a mole of water molecules in here. Okay, now think about it. This is the thickness of a dime. This would be pretty equivalent to the volume needed for 1 mole of water molecules. How big is a molecule? Pretty tiny. Yeah. We don't even have technology that can look at atoms yet. Okay? So we don't have that type of technology. But again, this thin dime we can see, or barely see. And if we stack up 6.02 times 10 to the 23rd of these dimes, it goes way across, actually 1.5 times our Milky Way galaxy. So, number one, a mole is a big value, and when we look at molecules or atoms, they're really small. Really small. Okay? And that's what that's getting at.
Sorry.
So, it's a big number, and atoms and molecules are really small. All right, the mole and molar mass. Looking at your periodic table, okay, we finally get to use these numbers down here. Okay, up until now I'd said don't even look at the numbers on the bottom. Now we get to. We're going to start using those values. We've been using the number on the top left. Again, the number in the top left corner of the box represents what?
Number of
Protons, or the atomic number. What are these numbers here? The charges. We did that last topic, excuse me. And so now we get to use what's called the molar masses. Why are these decimal places, or have decimal points? What are these masses for? See if you can remember this. It's been since before Christmas that we talked about it. It's the average of all the isotopes. In other words, if I look at, say, copper probably has some isotopes, and again, isotopes are just in different numbers of neutrons, same number of protons. So we have some samples that have a mass of 59, 60, 61, 62, 63, 64. There's many different isotopes. So it's the average of all of those isotopes. So for the most part, they should all have a decimal. Now, if you see something like this, that's an approximation. They haven't really figured it out yet. They're just guessing on that. And especially on these man-made ones down here. Good news is we're not going to use those or that one. Okay, so we'll stick with our 52. All right, so this is the amount of grams that we'll say if we had 6.02 times 10 to the 23rd atoms of nickel. That's how much it would weigh. Okay, so that's how we're going to use those values in the periodic table. So looking at this, because 6.02 times 10 to the 23rd is too large to count one by one, I'm not even going to have you do a calculation if you could count each atom 1 second at a time. You'd probably be dead before you got to the end of that project. Counting the mass or measuring the mass is a much easier way to determine if you have that value or not. Okay. We could also, we do this in our everyday life. If I knew that I had, say, a pop can, and let's say that each pop can weighed 10 grams, or a Coke can, Diet Coke can, whatever you want to call it, and say I had a bag of cans, and I put it on the balance, or on the scale, and the scale reads 1,000 grams. Can we determine how many cans we have? Yeah. So you just take the mass or the known, and then it's just factor labeling. So we take the mass that we know, divide it by the mass per can, that'll tell us how many cans we have. That's what we're going to do with atoms. That's essentially what we're doing today, which isn't too bad. What's that? Should be easy. Okay. When we talk about molar mass, we're talking about the mass per mole. Okay. So when you hear me use molar mass, and I'm referring to these values here, these are the molar masses for the respective elements. And we'll use the average for those molar masses. Okay. Molar mass is the weight in grams of 1 mole here on planet Earth. Obviously, you know it would be different anywhere else, but good news is I don't care about anywhere else but here on Earth. So we'll use the weight here, and we already know that 1 mole contains 6.02 times 10 to 23 entities. Therefore, the molar mass is the mass in grams for 6.02 times 10 to the 23rd entities. The molar mass of a substance is the molar weight. Atomic mass unit, which I will rarely use this topic, okay, or 1 AMU is the mass of 1 atom. Don't worry about that. We're going to be using grams from this point on. But if you ever down the road in your chemistry career you hear about an AMU, that just means it's an atomic mass unit. Okay. And let's see here. I think that's, oh, this one last blank here. Therefore, the periodic table, to get the molar masses, every element has the same number of atoms in a mole. So what that means is, if I gave you 55.85 grams of iron, could you tell me how many atoms you had? Yeah. Okay, iron here. So we could do some calculations, and we'll do that today. Okay. All right, let's do a few conversions here. Let me check before I turn the lights on if we have any other blanks. No more blanks? Oh yeah, you do right there.
Oh, we're still going?
Yeah. Yeah, we're just going for molar mass and then mass of a compound. Okay. Now, the molar mass for an individual element, yeah, pretty simple. However, for a compound, what we did last topic or back in Unit 5 where we wrote out the formula, we'll do some examples where we find out the total molar mass of the compound as well. And here's an example here. In this formula, NO2, nitrogen dioxide, you have 1 atom of nitrogen, you have 2 atoms of oxygen. We'll find out the molar masses for those. And it'll be a little easier once we do it. And let's see, and I think, yeah, that's it. So let's, it's the same thing. Just want to make sure we have the blanks there. No, we don't do molecules today. I'm sorry. Okay. So we're just gonna do these. I'm gonna turn the lights on. Do have your periodic table out, because I won't be able to reference that while I have this off. Now let's go turn the lights on. All right, I think we're on. Let's take a look at page 4. Yeah, let's look back at page 4. And it says, let's do a few molar conversions. It says, the first one says, find a number of moles in grams. Find a number of moles if grams is given. So number 1, it says, how many moles of magnesium is in 96 gram sample? So again, just like with factor labeling, always start with what you know. So we know we have 96 grams of magnesium. What's the symbol for magnesium? Mg. Okay.
Do you
So
have to put that 0.0?
did I? Oh no, you don't have to.
Okay.
Okay. So again, what we're going to do is we're wanting to go to moles. So like with any factor labeling, if it's not the unit you're looking for, we're going to move it diagonally. Now we'll put a number there in a second. So we're looking for the number of moles of magnesium. What number do you think goes here? 24.3. Where'd you get that? From the periodic table. Good. And then since that's the unit we're looking for, grams will cancel out. And whatever that value is.
3.95.
There you go. And that is moles of magnesium. Okay. Number 2. How many moles of nickel are in a 25 gram sample? Okay. Go ahead and try that one on your own. And don't peek up here. Everybody good? Bless you. It will get more interesting than this, I promise. Number 3, it wants to know how many grams of copper. Okay, so I gave you grams to start off with. Now it wants to know the number of grams of copper if you had 2.5 moles of copper. How do I start that?
The mole.
Yeah, so we'll start with what we know. So we have 2.5 moles of copper. And since we're looking for the mass, we're given moles, so where should moles go in this problem? Diagonally. Good. So 1 mole of copper weighs how much? Good. So again, this brings us back to our factor labeling, the good old days. Oh, we missed you so.
How many decimal places should we run to?
3 sig figs is always a good idea. Okay. Now I know my calculator said 158.875, but get in the habit of showing 3 numbers. Okay, think you all could do that? Piece of cake? Alright. Now for the fun things. Turn to page 5 at the bottom there.
Wait, Craig.
Yeah.
For number 1, why did you put the MG?
And if you do include that, that's fine, but definitely have the mole. Okay. Let's take a look at the practice problem at the bottom of page 5. It says calculate the mass of 1 mole of each of these substances and then name each. So number 1, we have this MgC2H3O2 with a 2 there. Anyone know what the name of that is? Good, magnesium acetate. So with the compounds, what we're doing is we're simply just adding the masses together. So you have to ask yourself, okay, well, how many magnesiums do I have? There's one there. And looking at your periodic table, the molar mass for magnesium is 24.3. And then we have how many carbons? Good, 4. So 4 times the 12.01. Hydrogen, we have 3 times 2, which is 6. And it looks like this. And oxygen, we have 4 of those. And that all equals something. So the nice thing about this is just find out how many of each element type you have in there, and then look on the periodic table for the molar masses and multiply. Now when entering this in on your calculator, the calculator is going to respect how you enter this in. So this plus this times that, plus this times that, plus this times that, it'll respect it because, again, order of operation. So looking at this, so you get a value of 142.388. Now again, this is the molar mass for magnesium acetate. So what we don't want to do on this one is round this, because typically you'll do something with this value, but everybody else showed 3 sig figs. Okay. And again, so if I had 1 mole of magnesium acetate, it would weigh 142.33 grams. Good. Let's look at the next one. So we have this one. This is not one of your polyatomics. It's oxalate and it has a -2 charge. Again, you're not going to need to know that, but if I were to give you the formula, I would hope that you would be able to figure out the molar masses. So again, we have 2 aluminums, and each aluminum weighs 26.98 grams. Plus we have how many carbons here? Good, we have 6 of those. And how many oxygen? 12? Good, good. And so again, just add all those up. And you should get around 318.02. So again, for 1 mole of aluminum oxalate, it will have a molar mass of 318.02 grams per mole. All right. Number 3. All right, on there, it's in word form, and again, that's what oxalate is. So we have calcium. Oxalate has a -2 charge. Aluminum has a +3 charge. So calcium has what charge? Good, +2. And the oxalate looks like that. So +2 -2, that equals 0. So make sure that if you're given a word form that you actually balance the charges. Again, that's what we did on the last test and back in Unit 5. Continue doing that. We don't want to stop ever doing that. All right, so calcium, we have 1 of those, which is 40.08 grams, plus 2 carbon, and 4 oxygens. So again, that all, and should give you a value of 128.1. And again, if I had 1 mole of calcium oxalate, it would weigh 128.1 grams. Try the last one on your own and make sure that you read the formula correctly, all right? Everybody good? Alright, let me pass out the homework here. Take a look at your homework sheet. And the top part is what we just did for the examples. I want to work out the first one in the middle section and the first one on the bottom section. Let's take a look at that since I didn't have one of those for the examples. So the middle section asks how many grams are in each of the following mole amounts. So you were given 1.60 moles, and that's of mercury, looks like mercury 2 nitrate. Okay. So it wants to know how many grams. Okay. So again, like always, start with what you know. So we know we have the 1.60 moles of mercury nitrate, actually mercury 2 nitrate. If it's not the unit you're looking for, in other words, we're not looking for moles, we're actually looking for grams, put mole down here. And what we'll always do whenever we're doing molar mass, we always want to find the molar mass per mole, so 1 mole. So what we would not do is put 1.6 down here. Don't do that. Just make it per mole. So when I look at the molar mass of something, so like for carbon, it's 12.01 grams per mole. However, since we have a compound here, we want to find out what that is. So let's just do like what we did. So mercury has a molar mass of 200.59 grams. And we have how many nitrogens? Good, 2 of those. And we have a total of 6 oxygen. Okay. So if you want to, okay, I'm not saying you have to, you don't have to show this work here. If you're able to type it in and just put the value in there, that's fine. And typically what I'll do when I'm showing this type of work on the board is I will go ahead and type that in just to make sure everybody's on the same page. So this whole thing weighs, or has a mass of 324.61 grams per mole, okay? So per mole. So now that we have that, we can simply take the 1.6 times this value divided by 1. So you should get around 519. And since this is our final answer, if we're looking for grams, we want 3 sig figs. So that would be our answer there. If you just stopped at grams, that's fine. If you went ahead and put what it's for, that's okay as well. So, but you have to at least show the grams. Get in the habit of start showing 3 sig figs. We don't want to round our molar mass because typically we'll do something with that. Okay, so let's look at the second one, or I'm sorry, the third section down here, the first one there, where it says, the question says, how many moles are in each of the following gram amounts? So we're looking for moles now. And in this case, we have 64 grams of water, and it wants to know how many moles. Okay, again, let your units tell you where you're going. We don't put grams up here because if we did that, we multiply grams times grams, it'd be grams squared. So we're going to put grams down here, but don't put it down there just yet. We are looking for moles. We know that we're looking for we're looking for moles of water. Just like with here, okay, I can flip this and they'll still be related to each other. In other words, if I said 1 mole of mercury 2 nitrate has a molar mass of 324.61 grams, I could flip that and say that on top, if I had 1 mole of mercury 2 nitrate, it would weigh 324.61 grams. So these two things over each other, just back like when we did factor labeling, these are equal to each other. This amount weighs that much. Flip it, that amount weighs this much. Okay? So always do it per mole. So for 1 mole of water, do the same thing. That's 16 grams. So there's your unit of grams because we're adding the like units. The unit grams will go away. I believe that's 18.16. Okay. So the molar mass for water is 18.016 grams per mole. So the gram units will cancel, and let our calculator do some work here. So around 3.1 we'll say 5.5 moles, okay? And again, show 3 numbers in your final answer, or 3 sig figs. So I'm not worried about decimal places. You'll notice there's no decimal places here, but we do have 2 decimal places here. In both numbers or situations, we have 3 numbers.